In the previous video, we derived the so-called quadrupole formula that relates the gravitational field, which will be radiation field, with the quadrupole of the momentum of the mass distribution of a given system. Okay, it's given by this formula where t has to be evaluated at the retarded time. We also made an estimate of the size of the intensity of these waves for a system with a characteristic extension and the characteristic velocities and so on. We saw that this was a very weak effect, and we also at the end showed how Qij could be calculated for a system of mutually interacting particles interacting through gravity only. In this video we are going to work out Qij for the particular case of a binary system, so a system of that we will approximate by two particles interacting gravitationally. Instead of making direct use of the formula that we derived, we know that there are many simplifications that hold for the two-body problem. Okay, and remember that we are using essentially the Keplerian approximation for Qij. So we know that there are many approximations that can be made and many simplifications, and we are going to use all that plus the results that we know of the classical Kepler problem to compute Qij in a more explicit form. This will allow us to compute Hij, and with that we will compute the power of which is emitted by a binary system through gravitational waves. Okay, this means that this power means that energy is lost by this binary system, and since we know that the energy is related to the period of the bodies, okay, which are orbiting each other, then we can these periods will be shorter and shorter when energy is lost, and we will compute how this period changes with time. Okay, as you know, this effect has been observed in the binary pulsar. Okay, there is a very famous one which is called the binary pulsar, which was discovered by Holmes and Taylor. And it was first discovered, but there are many other binary pulsar systems in which the same effect has been also measured. And this effect provides indirect evidence of the existence of gravitational waves. So long before they were detected, it was their effects were already measured, okay, as energy loss by this binary system. As it is usually done in the Kepler problem, we use center of mass coordinates for the two bodies that and we call the coordinates xi1 and xi2. Xi will stand for the relative position, and vi here will denote just the derivative of this relative position, so it is the relative velocity. These positions are related to the relative position by simple formulas. Okay, so for 1 and 2, these are the masses 2 and 1 divided by the total mass, which is the sum. Okay, and the same happens, of course, for the velocities. You just take up, this has to multiply xi, and for the derivatives, which are the velocities, you get the same relations, or the same proportionality constant if you want. Okay, let's denote by r the absolute value of this relative position vector. So it is the distance between these two bodies, and let us call n I the unit vector xi divided by r. Okay, furthermore, we are going to introduce another parameter, which is the product of the two masses divided by m1 plus m2 squared. Okay, this is different from the reduced mass. The reduced mass and this parameter are related by mu divided by the total mass. Again, there is one more power of total mass here, and so this is dimensionless and is called the symmetric mass ratio. And this is the reduced mass. Remember that the reduced mass is just the quadrupole momentum is just qij. Then remember there was a sum over the masses with the products of their positions. So we have m1, x1i, x1j plus m2, x2i, x2j. And here is where we are going to use these relations. And the moment you introduce, okay, let's do it explicitly. This is m1, then you have m2 squared divided by the total mass squared, and here you see that you get eta times m2, and then the position as xi, xj. The same, but with interchanging m1 and m2 is going to happen to the other term, so we are going to get eta m1 xi xj, and together this is, well, common factor eta xi xj, m1 plus m2, so this is the total mass times eta xi xj. Okay, this is the kind of simplifications that take place in the two-body problem. Now if you take derivatives, this is straightforward, so I will not do it in full detail. You get this factor, and of course you get something with two derivatives, two terms with just one derivative, and another term with the second derivative of xj. Now, you know that in this two-body problem, it becomes effectively a one-body problem where the relative acceleration is given by minus g, the total mass, and this is the relative position divided by the relative distance cubed, and we can substitute here and here this, and okay, you get that this is equal to 2 times eta, the total mass, vi, vj, so this is just this term, vj, and then now the other term is really symmetrized at the moment because x2 with two derivatives becomes proportional to xi, so this is why you also get a factor of 2 and then divided by r and ni and j, which remember was xi divided by r. If you want, we can write this as minus g m dot ni divided by r squared. Now what we are going to do is to introduce, well, we are going to work in spherical coordinates, typical spherical coordinates that you work when you study the Kepler problem. And in those coordinates, and I, remember that we set theta equal to pi over 2, so this is a choice that we make. Then ni with theta equal to pi over 2 is this vector cosine phi sine phi and 0, while we are going to introduce something which is the derivative with respect to phi of ni, we are going to call lambda I, which is minus sine phi cos phi and 0. Observe that, okay, this is written as a vector. Observe that because ni is 1, as you can see, lambda I and I is equal to 0, okay, because ni is the derivative of this vector. So they are orthogonal, and well, lambda I turns out to be also 1. So these are two vectors which will help us to write anything in the plane of the orbit. Okay, any vector that lives on the plane of the orbit will be proportional to ni or lambda I. So in fact, as we know, for instance, xi is just r times ni. Okay, this comes from the very definition of ni. Then vi, you find as the derivative of xi, so it is r dot ni plus r, then ni is only a function of phi, so we take the derivative of ni with respect to phi, and we multiply by phi dot. Okay, and this is r dot ni plus r phi dot lambda I. And remember that phi dot is just L divided by R squared. Okay, now comes a long calculation. Okay, this is straightforward, but the only thing that you have to do is substitute the values of R for the Keplerian orbits and of phi dot is already given by this, so if you know what R is, you have it. So remember that R is just P, which is this semilatus rectum, E, which is the eccentricity, and cos phi, if we set phi 0 equal to 0. Here we are not interested in precession, so we just ignore phi 0, okay, from the beginning. Then when you take the derivative of r dot, remember that here since this is an implicit expression, r as a function of phi, okay, you have to take the derivative with respect to r and then multiply by phi dot. So first you would have Pe sine phi divided by 1 plus E cosine phi squared, but then you have to multiply by phi dot, which is L divided by R squared. But R squared is this, so you have P squared, and this expression squared as well. So these two things cancel, these factors of P also cancel, and you get LE divided by P sine phi. Okay, I'm not going to do the rest of the calculation. You can find it in the lecture notes. Okay, the only thing that you have to do is to write this using this and so on in this expression for the second derivative of Qij, and then you arrive at the following expression. So this expression, as it is a tensor in this is Ij, can be decomposed, and this is a tensor that just lives on the orbit, can be decomposed in these bases. Okay, here Ni and lambda j are symmetrized, And we have also introduced this capital R here because in the formula that gives us the gravitational field in terms of the momentum, there is this R, but this R looks like this R, and it is not the same R. This is the R, which is the relative distance between the two bodies, and this R is the distance from the source to the place where we are observing the gravitational wave. So we have to rewritten it as a capital R. Okay, and this is the expression, which is really a complicated expression. Okay, and I'm afraid when I cut this formula I suppressed the factor of chi, otherwise you never get G here in this form. So, okay, this is not what you are going to observe directly, okay, and what we are interested in this section is to derive a formula for the energy loss. So the way to proceed would be first you have to split this field into the two polarizations. So what you do is to write these two fields, which are the projections of this H bar with the two polarization vectors that I think we called epsilon plus ij and epsilon x ij. Okay, this gives you a common factor, and then two expressions that we are not going to write explicitly. You can find all this, by the way, in Poisson and Will's book. Okay, where this H0 is something that gives you essentially the strength of this gravitational wave. It contains this c to the 4 factor, another factor that depends on the distance, and this gm total square divided by p. Now, a calculation that we are not going to do, but you could study in Landau and Lifshitz book on classical field theory, and which is also derived maybe in a more complicated way in the book by Poisson and Will. You could say that the derivation of Landau and Lifshitz follows essentially the derivation by Einstein, and Poisson and Will is more sophisticated and maybe more rigorous. Well, certainly more rigorous. There was a lot of criticism of Einstein's formula. Okay. Then you can prove that the power emitted, okay, per solid angle is, with including all the factors of the speed of light, 3 derivatives of q ij with respect to time, and the projection, well, this could be emitted in each of these two polarization modes. Okay, and this square, this is per polarization. So when you sum over all the polarization, or the two polarization modes, what you get is that the power is given by this formula, integrating over the complete solid angle, ij q ij minus a third of 2 derivatives, sorry, 3 derivatives again, ij, sorry, the trace, square. Sometimes I cannot even read my own formulae. Okay, this is an expression that Einstein obtained in 1918. Okay, it received a lot of criticism, but following Poisson and Will, which is a more modern and rigorous derivation, you arrive essentially at the same result. Now we have computed Q double dot. Okay, so the thing is to take one more derivative and plug this that result here. Okay, we used Q double dot to obtain this, but now we can take one more derivative and substitute it here and find for P. And also you can average this power emitted over a full orbit. There is a classic reference, which is Peters and Matthews 1963 paper, and then there is another paper by I think it is Peters, and the references are given in the program with links to the original papers. So this power emitted on average over a complete orbit is given by this well, not so nice expression. Okay. G, this is the way it's written by Poisson and Will. Okay, this is because there is a nice expression for this combination, and then raise it to power 5. So in the end, this is a 1 over C5 effect. Then you multiply this by E1 minus E squared to 3 over 2, and 1 plus 73 divided by 24 E squared plus 37 over 96, ugly numbers, e to the 4. This is the time-independent formula that we want to use. And the simplest way to use it, it is, again, a very crude approximation, or as a first approximation, could be to understand that this is the loss of energy. Okay, this is just minus this average of power radiated, and plug into this expression for the energy of this equivalent particle rotating in the Kepler problem. Okay, and we know that this can be written in this way: eta minus eta g, the total mass squared, divided by 2a, where 2a is the semi-major axis. Okay, remember that a is p divided by 1 minus e squared. Okay, so with respect to dt, if the energy is given by this, and this doesn't change, the total mass doesn't change, so the thing that changes is the semi-major axis. So you just have to take the derivative. Minus with minus is plus, is eta g, the total mass squared is divided by a squared, and okay, you relate this with the variation of the semi-major axis with respect to time, and now this is equal to minus p, for which we have this complicated formula, and okay, putting everything together and simplifying, you get this formula that I'm just going to copy from the lecture notes, where this formula was itself copied from Poisson and Will's book. And then the next step is to use Kepler's third law, which relates the period with the semi-major axis. So P is just 2 pi and the square root of a cube divided by g total. Okay, you take the derivative with respect to time, which is the thing that in the end you are going to measure. This is nothing but 3 pi, the square root of a divided by g total, and this derivative of a with respect to t, and then you plug in this formula and you find something which is actually independent of a, but contains p. Okay, again, I just copy the formula from the lecture notes. And this formula is independent of A because if I've used this relation to rewrite it in terms of P. Okay, this gives you the fundamental law of variation of the period with time that you can integrate and so on and compare with the experiment with the observations. The only thing that we have not introduced here is this M, which is called the Chirp Mass. It's a parameter that appears very often, and this is why it has been introduced, and it is eta to the 3/5 times the total mass. Okay, this is the definition. And now, okay, again, you can integrate this formula, which is simple. This is just a power, and find how how P should vary with time. And what I'm going to show you is a comparison of the measure of the observed values of the period along several years from 1975 to 2005, and compare with the curve, with the theoretical curve, which is obtained from this at the first approximation, but which you can improve. Okay. This figure is not the period itself, but is represented by the period shift, okay, accumulative. So it's not the period shift per full revolution, but accumulated over the years. The red dots are the measurements, and the line is the theoretical prediction, which, as you can see, is extremely good. And basically, this is why this experiment, the experiment of the observation of how the period is changing with time in this binary pulsar, was awarded with a Nobel Prize in 1993. Really, if you can, if you associate, the reasoning here is very simple. These two masses in orbit irradiate the gravitational waves that at the moment you were not able to detect. You cannot detect them now either because they are still too weak. You can only detect them when they are at the final stages before merging. But you can detect or measure the indirect effects because the system loses energy and then the period will decrease. Okay, they will start getting closer and closer and rotating faster, orbiting faster around each other. This is, I think, this is one of the most impressive results of general relativity before the direct detection of gravitational waves. And it is also very impressive how they were able to measure this period, because you only see the flashes of the pulsars. They had to realize that there were two pulsars rotating one around each other and not just one. And they have also been able to measure the variation with time of other orbital elements like the eccentricity and so on. So I think this is the best measure of these orbital parameters.